Allora, in teoria, se vai sulla pagina, adesso siamo live, lo dovresti trovare. Tu hai già sulla pennetta? Allora, aspettate.
La prima.
L'ordine. Tu sei il primo, tu sei la terza invece.
No, io faccio delle circolazioni.
Ah,
Sicuro chiederti per informazioni.
no, scusami, mi stavo sbagliando.
No, non vuoi aggiungere altra?
Era il ragazzo, non pensavo che fossi un'altra persona che sono girata e l'altra persona, scusa. Nel senso...
E dicono che non potere l'organizzatore.
Scusate, sono un attimo stordito. Ok.
Ciao,
Nell'intervallo conviene chiedere cioè lo facciamo magari come ultima cosa di chiusura della sessione precedente. Diamo l'avviso che tutti quelli che devono parlare dopo vengono qua.
Comunque tutti con questo, non con loro. Vuoi implementare anche con loro?
No, facciamo un gioco questo qui in modo tale che siamo più rapidi nei cambi e non poi
le comunicare.
sì, no, è più complicato gestire altrimenti il video,
Ok,
che è un sistema un po' complicato. Ok, allora se le persone si mettono qua a parlare direi che si vede bene. Io devo ancora andare a recuperare un attimo le altre scatole in macchina. Ciao. Sì, hai già sulla pennina? Sì. Ok. Tu sei carratta? Ok.
Devi
Ciao. Sei il quarto speaker davanti.
Carlo, vuoi prestare la tua testa per mettere...
Sì.
No, a parte che
Ok. Sì, ti spostiamo all'interno della stessa sessione.
Luca, stavo pensando di chiedere a...
Ce la fai?
Luca?
Sì?
Stavo pensando di chiedere ad Armando. Adesso lo sento, lo vediamo.
Buongiorno.
Buongiorno.
Stamattina è stato più facile, dai.
Vero? Ci ho messo un'ora, sono dalle 7:10 sui mezzi pubblici, però...
Veramente?
Cioè, dalle 8:10. Ah, non c'è il gallo.
Ma noi abbiamo solo l'albergo qua vicino, meno male, in 20 minuti ci abbiamo messo a piedi.
Dove siete andati l'albergo?
Ionico. Ionico. Via Sirigella, mi pare.
Ah, di Sicilia?
Sì, esatto. Fermata a Torre.
Di sera è grande vita, vero?
Eh?
Di sera lì grande vita.
Ma...
C'è si strada,
vabbè, ieri siamo stati di poco, non è che...
Qualche
Da
problema
sera
non ci va. Qualcuno fatto male.
non so,
Ciao,
provo a...
Vabbè, io ce l'ho. Hai seguito le mie indicazioni, sei arrivato.
Mi sembrava assurda che... Cioè, ok, vedi i cartelli, ma
Si vede in un posto così.
Sì.
Sì, ma tu non sai le nostre, scusa. Quando abbiamo dato
No, in Gismondi non era ancora mai capitato.
Ma è capitato di
Senti, la estraggo e la rimetto. Perché me l'ha letta e però non me l'ha letta. Ma se te lo trovo su...
Allora, sono gli ultimi che chiamano di Oranza, quelli si
Forse questa è la prima attimo, perché io la frenavo un po'.
Perché a Cagliari non tutti volevano usare, ma c'era anche la gente che si registrava come associato.
E vogliamo lanciare l'inizio caricare lo schermo.
Ma guarda, adesso sta frenando, abbiamo lavorato con le funzionari registrate. Ora ragazzi,
Questo che è del settimo, e poi questo è Torino, sì.
a Torino non si pagava la fine, ragazzi.
No, però le fanno
Sì, sì, a Torino sono la vista.
ok, questo è di Torino e questo sono
Tanto poi il telefonino ce l'ho dato. Questo è
questo
è il
è
settimo.
Va bene, io ti metto come, diciamo, da quest'altra parte,
Quindi che c'è
ti metto come in alto così.
largo.
Infatti non sapere perché poi a girare.
No, ma non penso ci sia penso non ci sia assolutamente problema.
Io sono stamattina con la
Tu sei?
Margherita.
Margherita, sì.
Stiamo già
Sì, la iniziamo a caricare. Mi manca soltanto uno della prima sessione che è Luca De Paulis. C'è Luca De Paulis?
Comunque vi pare che sia
No, io sono a cena.
Ascoltami, ti puoi...
Dov'è?
Studente di Bologna.
Sì,
No.
sei live.
Sì, allora, ci dovrei scrivere che ma non è quella che si impara sempre. Come se stessi abbiamo un ritardo.
È perfetto.
Ciao a tutti, prova.
Scusate, io l'ho vista subito dallo schermo.
Sì, sì, ok.
È perfetto, no?
Sì, sì.
È tutto in onda, ragazzi.
Ho una
Trollata di aver
Ti
fatto
promuoviamo
la
l'anno
casa.
dell'anno prossimo. Abbiamo deciso, si fa a Bologna.
No, io sono d'accordissimo.
Sei
Vabbè,
d'accordissimo?
questa?
è quella, sì.
provo a tingare un po' di gente.
Non sai se
Voi ditemi che devo fare, che io lo faccio. Assolutamente.
Grazie.
Ragazzi,
Facciamo una dichiarazione live in diretta.
No, sarà un organizzatore.
le persone che parlano adesso nella prima sessione possono venire qui così
Noi ti seguiamo da
ho parlato un attimo con loro.
Se vuoi una capatina a Bologna la possiamo comunque.
Vabbè, per forza.
Cioè, non è che stai-
Ormai siamo affezionati.
Che cosa c'è a Bologna? A parte la portata?
Vabbè, c'è i tortellini, c'ha tanti bei posti da vedere. C'ha un caldo che si muore.
Vabbè, però c'ha quel coso, il food park, come si chiama? Quello che stanno pubblicizzando. Il food park, come si chiama?
No, la montagna.
No, ok, quello di Farinetti.
Quello grande,
È già
figo.
figo.
Sì, però non ci piace.
Lo vuoi fare a fico?
E allora
Non mi piace Farinetti. Vado come Farinetti.
però poteva essere un turco.
Come?
Poteva essere il Czech. No, però dai.
Vabbè, ci fa
Rafting nei canali, no? Probabilmente sono le
Bologna è un turco, era così.
Non so se ti chiedi.
Questi erano i tiri.
1000 euro.
Abbiamo ancora un quarto d'ora, grazie. Sì, sì, lasciali, guarda, c'è un computer.
Sul scientifico, c'è il dipartimento di fisica, è uno dei dipartimenti più antichi di Europa.
La prima università.
C'è il museo di Augusto Righi dentro il dipartimento. Augusto Righi che è stato defraudato da Mazzoni.
che parla di...
Sì, allora perché mi sono sbagliato, lui ci viene dopo. Viene alla fine della tua
C'è una
magari quando puoi anche introdurre tu se vuoi.
Quella all'aula spenta, mi pare che c'è il primo tempo.
Però c'è anche il primo esperimento di
allora
di interferenza
dai così lo
sì.
perché lui ci fa una presentazione particolare
quello che ci faceva, non so se anche a voi faceva
abbiamo tempo per interagire con chi vuole.
Matteucci.
Sì,
c'entrava.
L'idea è...
Beh.
No, allora...
No, si può.
Dindini? Perché vengono gratis.
Vabbè, c'è l'NFL.
Esatto.
Sì, certo.
Vabbè,
Ma
abbiamo il
c'è
gioco che abbiamo il Cifarelli che è presidente della SIA, presidente del centrofermi, qualche soldo c'è.
Quando arriva glielo chiediamo.
Ne parliamo?
No, io non sto scherzando.
Neanche io, ne parliamo bene.
Abbiamo ancora 10 minuti, poi magari
Mettetevi già nell'ottica che un meeting, magari Roma, perché c'è tanta gente, però mediamente un meeting costa circa 2.000 euro.
sì, adesso devo prendere c'ho il cartello dei 5 minuti
Se c'è, se non c'è.
e poi dove
Vabbè, secondo me sarò. Cioè, mo' per gli scherzi.
magari provo a farlo
Cioè, a voi non bene.
vabbè, calcola, io ieri ho fatto una casa di sessione di fisica della materia, quindi
Sì, sono quella cifra 3.000.
allora, mica
No, però secondo me sul
aiuto
comunque se
abbiamo
abbiamo,
questo
non dico facilmente,
Poi noi abbiamo già il progetto
possiamo
coordinata, nel senso beh, chi la pensava che il secondo giorno sarebbe riuscita? Io generalmente sono quella che deve instaurare il router per il successivo.
se no possiamo
Ma io sto spingendo
questo qui
Il dottorato
proviamo un attimo la prima.
Vabbè, l'hanno già fatto l'anno scorso. Esatto.
Ah, è bello. Non c'ero, non c'eri.
Cioè c'ero ma non c'entravo con
Però io ti ho visto.
Sì, io ti ho vista lì. Io avevo un poster solo l'anno scorso.
No, non era acceso semplicemente. Ecco, l'unica cosa magari di dirlo è la intuitivo.
Vero?
Vabbè,
Scusate, spoilerato.
Allora, io ho più anni.
E le cose sono...
Allora, le presentazioni sono 1, 2, 3 e la quarta mano.
È una mia opinione.
Io vado a prendere un attimo un paio di cose che c'ho in macchina, però dovrei riuscire a prendere.
Io sono stata tolta il primo anno la Sissa e il secondo anno la Sissa sono stata organizzatrice, quindi per carità. Bello.
Ma io sto bene.
Però alle 7 chiudono il battente, spacca Tuccio, Anna, il lattuccio, il tuttino.
No, vabbè, non per forza. Non per forza. Si vedono su Izza, e si possono fare quelle cose. C'è le Smith, in cazzo ci sono queste case.
Ah, sì.
Queste case in campagna che no, è bellissimo perché si chiamano Smith che vuole avere tipo 8 giorni, una cosa del genere, perché 8 giorni all'anno solo prima potevano aprire e vendere direttamente i prodotti che facevano in casa al pubblico invece che passare. E quindi prendevano queste frasche, queste ghirlande fuori per far capire lo smizza, cioè questa casa di vita lo smizza in questi giorni. Adesso non sono 8 giorni solo, sono più volte, però non sono fissi, sono case alla fine, in determinati, prima una, poi l'altra, a volte insieme, così ogni tanto, per qualche giorno. Si vengono i mangi, formaggi, salumi, vino orribile, però tanto, che costa poco, è bellissimo. Poi a volte ce ne sono alcune panoramiche che danno sul golfo, si vede tutta Trieste.
Bello.
Spettacolare. Quindi si può avere...
Sì. Di vista.
Però...
Beh.
Ecco.
Allora, io se per caso da un workshop alle CPP da morire. Cioè, prima non le scelte
No, ma che...
No.
Cioè, voi adesso se si va adesso c'è barco. Vabbè, poi scendi a barco, ci sono i baracchini lì sull'infinita.
Io ho fatto 4 anni qualche mese a Firenze, quindi facevo molto Firenze-Bologna, Firenze-Roma per lavoro. Insomma, è un po'. Nonostante che mi dico che però risulta bella, piacevole,
Sì.
open, si presta molto. E ti dirò che qua, perché non c'è un fatto un esperimento con il collega mi è piaciuta.
No, adesso
A Bologna, sì, dobbiamo
metterci
sei tu solo, qua, per esempio.
Vabbè, ma là immagino ci sono un sacco di gente che sono...
Hai persone...
sono lì già 80, quelli dei... Secondo me loro si mettono in mezzo quelli... come si chiama quella cosa? Sì, io sono andato a vedere. Sì,
lui forse sì, no, perché mi piace in generale.
Sì, se c'hai, ricordati anche di mettere a colleghi che eventualmente possono dare una mano, che servono, diciamo, per non essere, diciamo.
Buongiorno. Un po' sudati però, perché...
Ricordati, minimo 4 di 5, pensaci.
Dottorandi, va bene.
Sì, dottor, ma anche postdoc.
Ah, vabbè, allora a posto. Ah, ce ne abbiamo pure una decina.
Beh, più siete, almeno dovete lavorare.
Se magari se lo facciamo però, facciamo anche se ci facciamo. Sì, dai. Quindi trovano i pure un posto. Vabbè, ti posso spiegare. Non spiegare, è lì, a posto. No, io mi sono
Scusate, uno di voi è Luca De Paolis?
Cioè, no, perché un bar, ma così da te li fatti. Secondo me non so se vado Si vede che guarda, questa si di quella là. La scanistica. La scanistica. Poi ci metto qua più non ha senso. Sei no? Io sono la testa
Vedo che ancora mancano persone. Io direi almeno 5-10 minuti aspettiamo prima di iniziare. Tanto basta quello dei 5 minuti. Non so se poi quello dei 2 o anche lo stop. No, io mi alzo in piedi quando ieri
faccio 5-2 dai. Ah, è tipo countdown.
io mi sono sempre fermato a 2 quando ci sono nel dubbio dico di sentirsi. Sì, ah, sì, no, quello sì. Allora, sta sulla canale di YouTube ma sta un po' la possibilità, però se cercare su YouTube live. Bravi ragazzi, che vada
No.
scatti quello che i passi a me il microfono ci penso io stesso grazie che ci dai una mano.
Sono stata contattata. Allora, io ho sentito male la sostituzione. Allora, hanno sentito direttamente che hanno
allora, al massimo possiamo semplicemente spostare lei come prima e shiftare tutti i numeri, in modo tale che loro...
Sì, se no non mi fa sapere, sì, se no, perché magari sì, c'è una sola sostituzione, ma non credo che hanno le procedure perché non sono un numero o un numero si sanno
fatto male che vada al corpo in breve.
chi la presenta
Un'altra sessione di fisica analizzava
sì, non lo so, c'è qualcuno perché
no, l'idea era di far provare a qualcuno del io proverei Alessandro Lì.
Non ce l'ho vedere.
penso che magari per capire
Io ho sembrato anche i libri di abstract per studiare di
ma questo è nel savoir-faire dell'ottimo fisico,
vero?
cioè
Fisica.
che è tendente all'eccellenza. No, vabbè, però se metti in un altro dominio, tutti i domini che abbiamo, noi all'interno dei domini spieghiamo, ecco.
Ciao, però la risposta, provo migliorare. Perché non mi
Vabbè, ma se sta arrivando, tanto
penso di sì perché
c'è tempo fino alla...
insomma,
Lui dovrebbe essere tutto il primo per una
vabbè, io non ho ancora solo piccolo.
Ti prego, ti rispondi tu da quando stai andare, cioè.
Non credo che sia proprio loro.
No, cosa è il mondo di montagna?
No, perché dovevo iniziare a allenare. Non so se riusciamo. Era 5-6 cartelle pari.
Luca De Paulis c'è. E ieri c'era
sai cos'è che però ci piacerebbe che arrivasse. Ah sì, c'è. Grazie, perché stai no, no, ah no, questa no. È vero.
esatto, io lo so. Il gelato è magari se messo al minimo. Vabbè, vai. Provo a parlare.
No, no, vedi.
Questo ma le stai.
Il gelato?
Prova. Prova. Prova.
Okay, so let's start. So welcome everyone to the particle physics session. So we will start with a talk about dark matter research and the LHC and beyond by Guglielmo Frattari.
So good morning, everyone. Today I will talk about dark matter search at LHC. So the question is, why dark matter? Well, there are many observations, cosmological and astrophysical observations, that hint at the existence of a non-emitting kind of matter. And for example, one of those measurements are unexpectedly strong gravitational lensing of galaxy cluster. In fact, here you can see that the measured gravitational lensing cannot be explained only with ordinary matter. So from many observations, we know that the ordinary matter is about accounts for about the 5% of the energy density of the universe, while dark matter accounts for about 1/4 of the total. But the major contribution to the energy density of the universe is due to dark energy, which we don't know anything about it. So today's question will be, what is dark matter? And we will try to give an answer. To try to answer this question, we can make some hypotheses. So this kind of matter has to be neutral and cold. Neutral because it does not interact with photons, and cold because it has to be not relativistic, otherwise we cannot explain the structure of the universe. And we also have to say that the dark matter have to interact only gravitationally with ordinary matter. So first hypothesis will be matrix, but not those kind of matrix, but this kind, which are massive compact halo objects, which are, for example, black holes or brown dwarfs. But this hypothesis is ruled out by gravitational lensing studies, micro lensing studies. So the other hypothesis is the particle nature for dark matter. And if we try to make the hypothesis of a particle nature for dark matter, we have to assume that it should be stable or at least long-lived, because we assume that we make the hypothesis that it has been produced in the early ages of the universe. So if we see the effects of this kind of matter, it should have not been decayed. So there are many hypotheses of dark matter, like neutralino, axions, dark electrons, or gravitons, and many things. But today we will focus on WIMPs, so weakly interactive massive particles, which are one of the most studied candidates of dark matter. We can try to summarize every dark matter search, every WIMP search, with this diagram. So let's say that this is a kind of Feynman diagram where you can have you have the two standard model particles and two WIMPs. And if we order the time arrow in different sequences, we can find every different search of dark matter. Like if you go from right to left, you get the indirect searches where you look for the annihilation of two WIMPs into standard model particles like photons or electrons. If we do this way, so from top to bottom, we get the direct searches in which you look for a scattering of a WIMP with a nucleon. And you can try in this way to study the seasonal modulation of the signal, because the Earth is moving in the universe where there is this halo of dark matter. And last but not least, you can see here from left to right the collider searches, where you make the hypothesis that you can produce a pair of dark matter particles colliding standard model particles. And this is done at the LHC, at CERN, and the dark matter is looked for by the ATLAS experiment. So LHC and ATLAS, the ATLAS experiment, are our, let's say, microscopes. So we have here the accelerator complex of the CERN, where the particles are boosted up to 6.5 TeV of energy. They start from here and then go through here and through here, and finally in the main ring, where there are 4 main experiments, and one of them is the Atlas experiment. It's located at the interaction point 1, and the Atlas is a very big experiment, so it's like 44 meters long and 25 meters high, and in which the particles are along this axis and collide in the center of the experiment. So it's very important to notice that the initial state momentum of the collision is only along this axis. So in the transverse plane of the collision, you should have 0 momentum after the collision. So this is very important in our search. The Atlas experiment has many sub-detectors from the inner part to the outer part, and these are used to reconstruct properly all the final particles which are produced in the collisions. But you cannot reconstruct, of course, every particles, like, for example, the WIMPs, because we know that they do not interact with our experiment. So we are trying to see in the invisible. So to see the invisible, we should exploit some other features that we can see. And one of them is look for the missing energy in the final state. Because, as I said, on the transverse plane, the moment should be conserved. So we look for unbalanced events, in which we have, on one side of the detector of the transverse plane, one object, and the other side, we have missing energy. So we are looking for miss, so miss transverse momentum, which recoil against a high energy jet. A jet is a bunch of hadrons which are produced in a very narrow way, and they are originated by the process of hadronization of gluons and quarks. So here comes in which you have missing transverse momentum. This is, let's say, the transverse plane of our detector. And on one side, we have missing transverse momentum. On the other side, we have this jet. Okay, so we have many particles which are collimated and appear as a jet. So, but not only WIMPs produce missing transverse momentum, but also standard model particles, because we know that there are many processes of the standard model which have the same signature, and one of them is the production of a Z boson, in which decays in true neutrinos plus a jet. And so this process has the same signature of our signal we look for. So we have to estimate this background, and we look for the, let's say, an excess of events in the tail of our distribution, of which will be missing transverse momentum. So, and we look for an excess. So how do we select events? So we built, let's say, a signal region where the events are, in this signal region, the events are, we think that there could be some dark matter there, okay? So we do some kinematic cuts. So let's say we require a high energetic jet and a big missing transverse momentum, and let's say we put a veto on leptons or photons, because our model does not include leptons or photons, and we require then some additional jets and a minimum separation with the missing transverse momentum, because you can misreconstruct the jets, so they can produce missing transverse momentum. And our signal region has a background composition which can be summarized by this diagram, in which you can see that the main part is due to the irreducible background, so Z into neutrinos plus jet. We have to estimate this background in some way. And then there are other backgrounds which we can reduce with some kinematic cuts. So how do we estimate our irreducible background? Well, we introduce some control regions in which we know exactly what is happening, and then we can try to estimate the number of events in the signal region just using some normalization factors on the background. So these control regions are built inverting some lepton vetos, and the most obvious control region that we can build is the control region enriched with events in Z which became true leptons plus a jet, because this process is very similar to the kinematic of the search of the process we want to estimate. But since we do not have enough statistics to estimate properly the background with only these control regions, we use also a control region enriched with W plus jet events, in which you treat all the leptons as invisible particles. So you can try to emulate the background process you want to estimate. How do we estimate this? We say that in the signal region, we have a number of events of background, which is composed by many different processes, which are multiplied by a normalization factor. And also we have other processes, for example, the number of top quark production in the signal region, which is multiplied by another normalization factor. And then we have these two normalization factors, which are fitted simultaneously to many control regions, in which we control exactly the background, so we can try to estimate the similarity background. So here I show you some early range results, because these results are not obtained with the full statistics of the 2015-2018 data, but we have only 2015 and 16. So on the top of the slide, you can see two control regions, so the W new control region, Z into neon control region, and with the different color, you have different backgrounds which are in our regions. And on the bottom, you can see the ratio between the data, which are the black dots, and the Monte Carlo, and the background of the standard model, the Monte Carlo, the simulation of the background. And you can see we have pretty good agreement after fit. Here you can see that in the tail of the distribution we have low statistics, so the errors are bigger. And then fitting those two control regions with plus two other control regions, we estimate in the signal region the background. So we see that in the signal region, as I said, the Z in two neutrinos plus jet is the main background. So you can see that is on the top of this sum. And then other backgrounds are stacked on those backgrounds. And after you do the fit to the control region, you unblind the signal region. So you put on the background estimation the data, and you look for an excess of data into the matrix distribution. And you can see that after fit, well, we have really good agreement with standard model. So we don't see clearly a new signal, a signal of new physics, but we can try to do some statistical analysis with a benchmark model. So which is our benchmark model for dark matter search? Well, we introduced dark matter to the standard model with a simplified model, because we don't know what is it dark matter. So we start from easy thing. We introduce an easy part to the Lagrangian of the standard model, which depends only on 4 parameters. So the couplings of the dark matter mediator with quarks and with winds. Okay, so we have those two couplings which are fixed in the search. I do not have enough time to explain you why, but let's say that they are fixed. And then we have the other two free parameters, which are the mass of the dark matter mediator and the mass of the wind. Okay, so here is the result. So don't be scared, because I will explain this plot point by point. So first, you can see that on the axis there are the mass of the dark matter mediator here, and here there is the mass of the WIMP. So we perform a scan with different models with different values of the masses, and we obtain a result. So in this part of the plot, theory fails, because the theory becomes not perturbative anymore, so you cannot do predictions. Here, this red line is the line that shows you the values which can explain all the dark matter seen in the universe with only a dark matter mediator and a piece of WIMP. Here, there's this dotted line, okay, which becomes this red line, and this defines the official regime, where the mass of the mediator is lower than 2 times the mass of the WIMP. So here, the cross-section of our production is very low, and we don't have enough sensitivity to this part of the plot. And finally, there is this black line, which defines the values which are not compatible with the data we measure in the signal region. So every value of the mass of the mediator and the WIMP under this curve are excluded at 95% of confidence level. Okay. So these results are based, so as I said, early range results, but soon we will have full range results with, let's say, 4 times the statistics. So this contour will grow up. So after looking what we do, let's see what other searches do. So we have here, the same plane I showed you before, and the yellow part is mainly done by the search I showed you before, but there are other searches done by the Atlas experiment which cover up the plane, and we get great complementarity among different searches. But our results can be also compared to the direct searches results. So here on the right, you can see that this black line defines this area of the plane of the cross-section between the WIMP and the proton, and the mass in the plane of cross-section and mass of the WIMP. And here, the values are excluded, and the purple curve are the values which are excluded by the direct searches experiments. So what will be after run 2? After run 2, LHC will undergo some updates, and the collision will be much more good because the bunches of protons will be colliding better. But we will have many simultaneous collisions which will be superposing. So it will be difficult to build missing transverse momentum, will be a challenge. And the result, we try to estimate what will be our results with the full statistics of the end of the LHC era. So with 100 times the statistics available, we move from here, that is the result I showed you before, to, let's say, here. This black line is if we do not improve our knowledge of the detector in terms of systematics. But if we improve our knowledge of the systematics, we can move up to this green line, and we exclude, let's say, dark matter mediators up to 3 TeV and WIMPs up to 900 G. So time is up, and I show you how dark matter search with the Atlas experiment at the LHC, and show you that the monojet channel is a powerful tool to look for new physics phenomena, even if we don't know what is it. And new exciting results will be soon released. Here you can find, in the end, an example of one of monojet events. In particular, is the event with the highest missing transverse momentum measured in the 2016. Thank you.
Thanks a lot. Is it now? Should be on. Yes. Now maybe it's working. Thanks a lot, Guglielmo. Are there any comments or questions? Okay, actually I have one. So your final state is composed by jets and invisible particles. So at LHC there are lots of jets, so how do you trigger this type of events?
Yeah, so LHC is a dronic machine. So yeah, we have a lot of jets, but of course we look for high energetic jets. So we don't use a trigger on the jets, but on the missing transverse momentum. So we require a lot of missing transverse momentum, and then we look for a jet event. But the main discriminating variable is the missing transverse momentum, and we need to require at least 250 GeV of this missing transverse momentum. Otherwise, we have too many events due to the misreconstruction of jets. Because if you if you measure bad a jet, you have, of course, missing transverse momentum and dark matter.
Okay, thanks. No? Any? Okay.
The plots that you show just at the end with the exclusion of different possibilities and stuff, are those entirely, I think maybe you said this, but are those entirely model dependent? Or is there any way to show the results in a model independent way?
Okay, so this plot, of course, this search is model dependent because, as I say, you assume that dark matter, there is only one piece of dark matter, your mediator does not couple to leptons, and then you assume the couplings, as I said, these couplings here. So these results are model dependent, of course, but you can try to, let's say, put a limit on model independent searches, looking at the inclusive number of events. Or you do, let's say, you get all your spectrum of missing transverse momentum, you sum up all the events and count the events and look for, let's say, an excess with respect to the standard model. Or you can do this, not getting all the spectrum, but let's say taking from the first bin, you integrate and you look for an excess. You get the second bin, you integrate and you look for access, and you, let's say, you can do a limit on model-independent searches, like that.
Any other comment or question? Okay, if not, thanks again, Guglielmo.
So we move on now to the next talk, which is again concerning an analysis from Atlas by Giuseppe Carratta, who will talk about research about type 3 CISO electrons with Atlas.
Okay, you can start. Thanks.
Ciao everybody, I'm Giuseppe Carratta from University and NFM of Bologna, and today I will present you the search for type 3 CISO leptons with the Atlas detector at the LHC. First of all, very quickly excursus regarding the theoretical introduction to explain why we do this kind of searches. Well, we know that the elementary particles like leptons, quark, and the mediator of the forces, the bosons, are described by a very successful theory, the Standard Model, which is valid up to a certain energy value. We can see on with the plot on the right that the prediction of the theory, the gray band, are in agreement with all the data collected by the LHC using different value of the energy in the center of mass. Then the Standard Model is a very precise theory, which do very precise prediction, and it is verified by experiment. So, what's the problem? One of the problems on the Standard Model is due to the masses of neutrino, which is very, very small compared to the other of the charged leptons. This involves in a very precise fine-tuning requirement to explain this mass value with the Standard Model prediction. In this context, there are a lot of models which try to give an alternative way to explain this phenomena. One of these is the type 3 CISO, which introduces at least two extra triplets of EV fermionic field decoupling to the electroweak gauge boson as the Z and W bosons. And generating a neutrino mass through the kappa coupling to the X bosons and the neutrino. In this model, the EV leptons are called L plus minus for the charged leptons and N0 to the neutral leptons, and are assumed from the theory to be degenerate in mass. The analysis strategy is very clear and very simple. We started from the Feynman diagram predicted by the theory and applied some preselection scat to isolate from all the data collected by the detector only the final states, then the topology of interest. The second step is the definition of the analysis regions, where we studied the significance studies from the signal and the background events find the optimal cut to isolate a region enriched of signal events, the signal regions, and another one enriched of background event, the Standard Model processes, which is called the control region. Then we pass to the background estimation. The background can be of two kinds. A reducible background, studied by the data-driven technique, which are due to the fake leptons or the check sweep. And another one, which is the irreducible background, the Standard Model process, which are estimated with, using the cut count method, which is used in this analysis, or also the multivariate analysis. The last step is the statistical fit, where we combine the signal region and the control region. The control region is used to normalize the data to the background events to find eventually axis of the signal with respect to the Standard Model prediction. Well, If we found eventually an excess of the signal events with respect to the standard model process, we have a discovery. In the other case, instead, we can set the upper limit on the mass of the searched particle. This analysis is performed using the data collected by the LHC, which was already described in the previous talk. We can see just two words. The ATLAS is a multi-purpose detector, and with respect to the other detector at the LHC, its physics is mainly focused on the beyond standard model searches. Passing to the analysis, we can see that in ATLAS we already have a confnot for the TEP3CSO, which was published the last year using an integrated luminosity of 17 inverse femtobarn. In this paper, only the 2 leptons final states, which is this Feynman diagram, were considered. A new analysis is in preparation using the full run-2 data with an integrated luminosity of 114 inverse femtobarn. In this analysis, we investigate the other topology with 2 leptons, 3, 4, and more than 5 leptons. But in this analysis, only the left leptons and the electrons and muons are considered by now. The previous analysis, already published, is focused on the 2 leptons final states. This region was split in lepton flavor and change. In fact, in the table on the left, we can see the cut applied to define the 2 kinds of signal region, one with the opposite sign leptons pair, and another one with the same sign leptons pair. The main case used to isolate the signal events with respect to the standard model process are due to the case on the MET significance, where MET is the missing energy transfers, as also on the HT plus MET variable, where HT is the scalar sum of the all objects PT. In the plot above, you can see all the region defined in this analysis. We have 2 kinds of control region, one field of top event, another one with the boson event. The validation reason, which are not explained in this topic, and the signal region. The plot on the right is the distribution of the HT plus MET variable in the signal region. We can see that we have more signal events with respect to the standard model process. This variable, HT plus MET, is used to perform a fit procedure. Top and the boson backgrounds are used to define the control region used into the fit procedure. To this analysis, we used a range of mass hypotheses for the EV leptons from 200 GeV to 700 GeV. We strangely did not found any excess of this signal with respect to the standard model process. Then we excluded the mass value of the EV leptons below 516 GeV. The new analysis regarding the 2 leptons considered more signal topology and background process with respect to the confnot. For example, about the signal, we include also the decay channels with the Z and the X bosons. The EV leptons mass hypothesis range is extended up to 1200 GeV, and also for this analysis, the fit was performed using the HT plus MET variable, and top the boson standard model process are the main backgrounds. We can see here the distribution of the H3 plus MET variable in the control region of the opposite sign, same sign leptons pair. This channel is a full electronic channel. Studying this analysis, we found also a paper of the CMS collaboration performed on a similar analysis on the TEP3CSO, considering already the final set with 3 and 4 leptons. Combining all the leptons multiplicity, CMS obtained a lower mass limit of 815 GeV. The strategy is reported in the table on the left, where we can see, for example, for the 2 lepton final state, that CMS considered defined 4 different regions. One below the Z window mass, one above the Z window mass, one on the shell, and another one excluding all the leptons coming from the Z boson. Then we expect an improvement of our analysis, including the 3 and 4 and more 4 leptons final states. Then, passing to the 3 leptons final state, we considered 3 different topologies. One with a JIT veto, another one with a Z veto, and another, the last, with the called the Z region, considering the events coming from the Z boson. For the jet veto, the preselection cut applied are a requirement of a number of jet equal to 0 and a value of the invariant mass of the opposite side same flavor pair, that the leptons coming to the Z, more than 18 GeV. For the Z veto and the Z region, the cuts applied about the jet side are the same. Then we required a number of jets more and equal to, and invariant mass of the jet into the W window, then from 16 to 100 GeV. But if at least of this jet is a big jet, we consider the mass window into the X window, then from 100 GeV to 114 GeV. For the Z veto, we exclude all the leptons coming from the Z, then apply the cuts on the invariant mass of the opposite side same flavor lepton pair more than 115 GeV, the Z veto. Instead, for the Z region, we considered this kind of leptons into the Z window, then from 18 GeV to 100 GeV. To isolate the signal events with respect to the standard model process, we applied this cut to define the signal region. The more important cut are also, in this case, the HT plus net variable, the HT on the trilepton system for the JIT veto, and also the transverse mass considering the subleading as leading leptons, and the angular cuts on the delta between the leptons of the final states. Here we can see the distribution of the HT plus net variable into the signal regions, and also for these final states, the HT plus net variable is used to perform the fit procedure. And we can see, for example, in the plot below the distribution, which represents the significance, the signal with respect to the background, that for the Z region, we have a low significance, which is due to the standard model process coming from the Z boson, both leptonically and hadronically. The control region, instead, is, we can see here the distribution of the invariant mass of the trilepton system. The boson is the dominant background process in these final states, and we can see a good agreement between the data and the Monte Carlo prediction. Then the 4 and the more than 5 leptons final states are reported in this slide using the Feynman diagrams, and we can see that here we have a very low statistics, but the channel is very, very pure. It is due to the low standard model process, which is considered the 4 and the 5 leptons into the final states. For example, to define the signal region of the leptons, we applied no cuts with respect to the preselection because there are not a very few standard model processes considering 5 leptons into the final states. To the 4 leptons region, the main cut on the invariant mass of the 4 leptons is the cuts which isolate the signal events with respect to the backgrounds, and also the max significance remove a lot of background events. Then, in conclusion, you can see that for now, all the analysis region for all the channel and the lepton multiplicity are defined. We identified the background samples floating in the fit for all the channel, which are the top, the boson, and the raised top process. And we can found also the variable which is used to the fit procedure. And in the plot of on the right, this is the fit, the results of the fit procedure. And here we combine the 2 and the 3 leptons final states, obtained an expected limit of 814 GeV. Then we are ready to combine all the channels into the fit. Well, stay tuned and brace yourself. EV leptons are coming. Thank you.
lot, Giuseppe. Are there comments or questions? Okay, now I have one. I was wondering if there were any studies about the perspective of this analysis when you go to the high luminosity LHC, or I mean, if you would prefer to have a high lumi or high energy, higher energy, let's say.
The problem is that with the high luminosity, we will increase the integrated luminosity. Then we can have a more precise analysis, but to discover this kind of particle, we require a very low energy. It's not the case of the high luminosity, because we increase the energy in center of mass of only one TeV.
Any other comment or question? Okay, if not, let's thank again Giuseppe.
Thank you.
And let's move on to the next talk about I think it's yes. Roberta Pillera, and she's going to talk about the fast muon tagger method for the imaging air sharing telescopes.
So, good morning, everyone. I'm a master student from. So, as I was saying, I'm a master student of Bari University, and today I will talk to you about my thesis topic, a fast muon tagger for imaging atmospheric Cherenkov telescopes. So first, I will briefly introduce you the imaging atmospheric Cherenkov technique. Then I will tell you about the Cherenkov telescope array project and the calibration of the optical efficiency of the telescopes using muons, focusing on my topic, that is muon timing. So the imaging atmospheric Cherenkov technique exploits the Cherenkov light produced by charged particles in extensive air showers in the atmosphere. They produce a light cone peaking in the near ultraviolet region of the spectrum, and this cone has a light pool of several 100,000 meters squared. And it has an angle of about 1 degree, and these UV flashes are very faint and last for about a few nanoseconds. In the corner, you can see an example of a shower image generated by a gamma ray. And the shape, of course, depends on the nature of the particles, because also hadron, in fact, we have mainly hadron showers, they have a different shape. In order to do astronomy, we are interested essentially in gamma rays. So for us, the hadron showers are the background. So here is a brief explanation on how this reconstruction of the shower works. The telescopes are deployed on an array, and the goal is to reconstruct the primary particle energy and direction. This is done using a stereo reconstruction technique. So each of the telescope records its image of the shower, and all images point to the shower core, and from that we can get the direction of the particle. Fitting the shape of the image, we can get the energy of the primary, and the background rejection is done using boosted decision trees. The first ICTs was built in the 80s, but the main ICTs today are Magic, Veritas, and Hess. They don't have more than 5 telescopes in the array, and the strength of this technique is to have a large number of telescopes. So the next generation ICT observatory will be the Cherenkov telescope array. It will be in 2 locations, so in the 2 hemispheres, in order to provide full sky coverage. The first one will be CTA North in La Palma on the Canary Island, and the array will have 19 telescopes. And the second one, CTA South, will be in the Atacama Desert in Chile with 99 telescopes. So the Cherenkov telescope array observatory will have improved performances with respect to the current generation ICTs in terms of energy range, field of view, and sensitivity. So the observatory energy range will be from 20 GeV up to 300 TeV. This is done using different kind of telescopes with different sizes, deployed on different subarrays in order to match the light pool of different energy showers. For the lowest energies, we have the large size telescope that will have a mirror of 23-meter diameter. And they will be located on both sides. There will be 4 of them on the core of the array. For the medium energies, we will have the medium-sized telescope with a diameter of 10 meters. They will also be on both sides. And then for the highest energy, we will have the small-sized telescope that will be only in the southern side. And the array will have 70 telescopes and will cover an area that is larger than 1 kilometer squared. There are currently different prototypes for each of the telescopes. We have 3 for the SSTs, 2 for the MST, and the first LST has already been built in La Palma and is now under commissioning and taking data. So the calibration of the optical efficiency of the telescope is done using muons. Relativistic muons at sea level have produced Cherenkov effect. They produce a light cone with an angle of about 1.4 degrees at the altitude that doesn't vary a lot with respect to the altitude, and they're usually particles at ionization minimum. Muons hitting directly the telescope, as shown on the picture, are called local muons. The image of these particles is a ring-like image, as shown in the simulation on the slide, and muons produce a known amount of Cherenkov light. That means that it can be computed analytically. So from the geometrical parameters of the ring and the observed light intensity, it is possible to get the optical efficiency of the telescope. So in order to do this, it is important to flag muons at a very early stage at camera server level. So here comes the necessity to develop a faster muon tagging algorithm that has to match the trigger rate of the system. As mentioned before, also for muon identification, the main background are proton shower images. So in my work, I studied muon tagging algorithm for 2 different cameras. The first one is CHECK, that stands for Compact High Energy Camera, and it's a design for the SST prototypes. It's a very small camera with square pixels and an expected rate of that goes from 0.5 to 1 kilohertz. And it is equipped using silicon photomultipliers as photon detectors. The second one is the current camera of LST Cam. It is quite different with respect to CHECK. It's larger and it has hexagonal pixel, and the trigger rate for LST is goes from 10 to 15 kilohertz. So in the first part of my work, I studied and tested different algorithms for CHECK. And in the second part of my work, I applied the best performing one to LST. So for CHECK, the idea was to find an algorithm that could be used as a muon trigger. So in the picture, you can see a simulation example of muon and proton shower. And comparing the trigger images, we can see that the amount of fired superpixels is comparable. And I studied discrimination algorithm that had an efficiency larger than 90% and a computational speed compatible to the expected rate. I cited the circle fit procedure using the Taubin method, a machine learning approach using a neural network, and in the end, a majority algorithm that consists in putting a threshold on the number of triggered superpixels. On the table, you can see the performances of the two methods, and the majority had the best one with a speed of 103 kilohertz. So a problem that has to be considered on this method is the stability with increasing night sky background. You can see the same muon simulated with different NSP levels. The NSP increases with changing the observation region. In fact, a low NSP corresponds to observation in the extragalactic field, medium one to the galactic plane, and a high one to the galactic center. This can, of course, affect the selection efficiency. However, studying the performance of the majority, putting a threshold on in order to have 90% efficiency at low NSB, we can see from the green plot that the overall efficiency remains above 90%, even with increasing NSB. So majority seems to be the best performing one and the most suitable one for a muon trigger. Now let's switch to the LST analysis. LST has is a very large telescope with a 23-meter diameter. So there is no strict necessity for a muon trigger. So, because the muon flux is sufficiently high. So what is done is usually an offline muon search. And for the identification of this muon, a precise fitting procedure is applied to all images in the run. And this is, of course, a very slow procedure and computationally expensive. So the solution to speed things up is to apply this muon preselection algorithm developed for check in order to find the potential candidates and to apply the fitting procedure only on them. So, however, I applied a slightly modified version of the majority. Indeed, not on the triggered pixels, but on the size of the image. The size is the sum of the photoelectron content of all pixels of the image. You can see from this example of simulated muons that a good full muon has a size of little less than 4,000 photoelectrons. On the bottom, you can see the preliminary plots of this efficiency analysis, and the size distribution are quite well separated. And choosing a proper cut, we get in the range from 2,000 to 3,000 photoelectrons, we have quite good values of efficiency and purity. So here is a summary of the speed performance tests I did on this algorithm. I applied the preselection procedure on a realistic Monte Carlo sample, and the preselection brought to a reduction to 3.5% of the initial amount of images. And after this, applying the fitting procedure brought to a reduction to 0.5% of the initial images. This shows how powerful the preselection is, because in a realistic sample, only 0.5% of events are good and useful muons for calibration. So it would be a large waste of time to apply such an expensive procedure on this large amount of events. So the preselection leads to a reduction of the time up to 80%. So the average event processing rate of the algorithm is 27 kilohertz. That is more than compatible to the expected rate of LST that goes from 10 to 15 kilohertz. So this opens up new possibilities for this method to be applied for muon flagging directly at camera server level. So jumping to my conclusions, concerning the analysis for check, the majority technique seems to be the most suitable one for a muon trigger, both in terms of efficiency, speed, and stability with increasing night sky background. It can be also efficiently applied as an offline preselection method to speed up the muon analysis for LST. But in the following, it will be also applied as a flagging at camera server level. And right now, the Czech prototype and the LST telescope are currently taking data. So an application and a study of this method is on real data is what I'm doing right now. So that's it. Thank you.
So thanks a lot, Roberta. Any comment or question? Okay, I have at least two. I was wondering, so when you were saying that the majority technique is better than neural network, so did you, I mean, or other people try any other machine learning technique that is not neural network that might be faster or?
Okay, we tried also to apply the support vector machines, but there was no significant increase in speed. But in the end, we abandoned the idea of machine learning because it's too complicated to implement it on hardware. This is very simple and very easy to implement. It's just a threshold. So that's why we opted for the majority in the end.
And sorry, I have another question about the majority technique. So I was wondering if you did any study about channels that would, I mean, be broken in the future, so to adjust the majority counting or the amount of it, well, the charge collection at the end you're doing in the construction.
Yeah, yes, this is something that will be done in a later part, because first we have to see how well actually muons are seen with the small size telescope, because this kind of small telescope are new with respect to the current one. So we're not really sure that muons will be seen as good as in simulation. So if this will actually work, and there are good hints that it can be done, we will refine and do a better and more complete analysis of the method.
Thanks. Any comment or question? Okay, if not, thanks a lot again, Roberta. And let's move to the last talk of the session, which is from Luca De Paulis about an experiment looking for the violation of the Pauli exclusion principle for electrons.
Hi, can you hear me all? Yeah, okay. Today I will show you some important results got with this experiment, the BIP2 experiment, which is looking for the violation of the Pauli exclusion principle. I'm speaking on behalf of the collaboration of BIP2, which is located in the National Laboratory of Frascati, which you will see tomorrow. And I also quote the National Laboratory of Gran Sasso because the experiment is located in this particular laboratories. So in this talk, I will start talking about how it is possible to investigate this Pauli exclusion principle. To be shorter, sometimes I will use PEP with BIP2. I will talk about the BIP2 experiments, proposing apparatus. I will show you the calculation of the new upper limit for the Pauli exclusion principle violation probability of electrons in copper, got with this data acquired until July of 2017. And at the end, I will show you something about this random walk, which is a new walk, solve a new model which we are using to calculate this limit, and which will give us, I think, a great and important improvement of the limit which we have. Sorry, okay. So let's start talking about how it's possible to investigate this Pauli exclusion principle. We know that in quantum mechanics, the Pauli exclusion principle can be formalized starting by two fundamental principles. And the first is that all states, including those related to the identical particles, are described in terms of wave function. In a second point, we can say that bosonic and fermionic states have a different behavior in relation to the application of the exchange transformation of identical particles. The former are symmetrical and the latter are antisymmetrical. In a paper which is quoted below in the slide, Messier and Greenberg highlight how this second superselection rule does not appear as a necessary feature of the quantum mechanical description of nature. So in this paper, they say that state of mixed symmetry could therefore in principle exist. And this means the possible existence of particle states that follow a different statistic than the fermionic or bosonic one. To conclude this introduction part, I want to quote Greenberg, which is one of the pioneers of the parastatistics studies. In a conference of 2004, he says that the possible violation of the Pauli exclusion principle could be due to violation of the CPT, violation of locality, violation of Lorentz invariance, extra space dimensions, discrete space and/or time, and non-commutative space-time. So we know something more about this theory, but how is it possible at the end experimentally test this Pauli exclusion principle? The experimental method which we use in BIP2 is based on the introduction of these new electrons in a copper bar by applying an electric current. Because, as Greenberg said written in one of his papers, whenever an electron is captured by an atom, a new state is formed that can have a certain probability of being a mixed symmetry state. And this state is highly excited, and from its decay, one could observe a possible transition prohibited by the Pauli exclusion principle. So we have as experimental goal the search for X-rays from Pauli exclusion principle violating transition. In BIP2, the target is composed by copper, so the energy transition which we are investigating is the K alpha 1 8.05 keV, and the forbidden one should be around 7.74 keV in copper. This value has been calculated using a program which uses the multi-configurational Dirac-Fock method. All the calculations are published in this note from LNF, and practically this a little bit decreasing of value is at most due to the fact that there is one more electron in the shell of the atom when there is this transition prohibited by the Pauli exclusion principle, as you can see in this schematized drawing here. Okay, so the experiment. We built this important chamber of experiment for the experiment, and the target is composed by these two strips, 10 centimeter for 1 centimeter for 50 micron, connected to an external generator by 2T copper bar, in which there is the possibility to make flow out of a current of around 100 ampere, and the temperature of the target is setting to 20 degrees, but it's, there is a water circuit which cools the temperature to not have a great rise and to not compromise the work of the detector which are used inside this apparatus. Here we have the target, which is schematized here. Near the target there are the detectors, and this whole structure you see here are the 32 scintillators, which are used for the veto system, and I will talk about it some slides after. But now I want to talk about this detector, the silicon drift detectors, which are very important for us work because are responsible of this measurement of energy which we want to do. Two chips containing 3 cells of 100 millimeters square of active area each. These two kind of chip made with these 3 cells are put near the target, and they using a lipid argon are cooled to a temperature which is around 100 Kelvin, and to have obviously a better performance in terms of energy resolution. The energy resolution was tested using a source of iron 55 through a 25 micron T plate to have the lines of K series of titanium and manganese to calibrate the spectrum, and we estimate a resolution which is about 150 electron volt around 6 keV, is around 180 electron volt in the range which we want to investigate for the violation. And also this SDD provides information on the radiation energy and timing, and this is very, very important because we testing this SDD respect to some scintillators with 2 nanoseconds of time resolution in the Stefan Mayen Institute of Vienna, get this very important result of this 400 nanosecond of full waveline maximum, which is sufficient temporal resolution to discriminate the background events. And this permits us to build this veto system, which is shown in this photo. I hope that it's visible, but practically is this one, which is composed by this 32 plastic scintillator measuring 45 for 3 for 3 centimeter cubic, and covering a solid angle which is around more than 90% in the structure. So we have the active shield allows to reduce the background in the range of the ethers of about 1 order of grandness. 1 order of grandness more than what is doing the lab, because the National Laboratory of Gran Sasso, for who not know it, are located inside this Gran Sasso mountain, which is in the center of Italy. And in this slide, I want to highlight how much is important this for the background of us experiment, because you can see a test done with 2 CCD and normalized distribution. And what I want to show you is that if you see the LNF, the National Laboratory of Frascati, with shielding of these 2 CCD, measure a background which is of about factor 20 more than what we get at the National Laboratory of Gran Sasso. So the background is reduced by a factor which is around 20 working inside the lab. And this is very important for an experiment which want to do a very, very precise measurement as VIP2. So at the end, VIP2 experiment, which is obviously VIP2 comes from an upgrade of this machine, which was BIP, which get this result, which you can see here, 4.7 for 10 to minus 29. We have a more compact system, which improved the acceptance, new target, which I talked before, different cooling system for the target. We use the water to not have a great rise of the temperature on the target. The current is 100 ampere, before was 40 ampere. We are studying a nitrogen flushing to reduce radon in barrack, because underground, as you know, the radon is it's inside the air, so it's very complicated to isolate that background. So we want to remove it from the barrack in which there is VIP2. This new detector gives us a very important improvement, because we have and the resolution which is practically the half of the resolution which we had before, and also the veto system gives us 1 order of grandness, and the expected data acquisition will be 3-4 years for this experiment. And formalizing all this in a table, we want to get a limit which is which should be around 10 to minus 31. Here I show some photos of the apparatus. Here you can see the boxes. Inside the box there is VIP2. This is before we install the external shielding, which is composed by copper and an external part of a lead. But this should comprehend all these parts. So to show it, I make some pictures before. And at the end, as I promised at the at the beginning, I show you some results get analyzing data. This is the spectra, the spectrum in which you can find the spectrum acquired with the current and spectrum of background, in which there is no current on the target. And from the subtraction of this spectra, one can get this number, which is the number of counts in the range of interest for the violation of the Pauli exclusion principle. And from this, normalizing to the 82 days of data taking, we get this limit in which beta square half is a factor which comes from the statistic of Vignac and Kuzmin, and they represent the probability of violation of the Pauli exclusion principle. So we set a new upper limit of this this Pauli exclusion principle for electrons in copper, which is 1.87 for 10 to minus 29, which, if you remember well, it was 4.7 for 10 to minus 29 here in the previous apparatus. So the thing is that, that in the 82 days of data collection, we get a result which is better than the 3 years in which DEEP was taking data before. So it's a great and important improvement. All details in this thesis of my colleague Andreas Pichler, if you want to evaluate. And also, at the end, I show this random walk, which will give us more and more important results, because in the LEAP experiment, the experiment below, the theory of this electron which moved through the target was practically calculated using this ratio between the linear length of the target and the average free electron path. But it's a very approximative method, because it's impossible to think that this should be the the real path of the electron inside the material. So with this method, using 7.5 centimeter of target and 40 nanometers of free electron average path in copper, we get 2 for 10 to 6 scatterings of a single electron. But the real mode which we are using now is the random walk, in which this electron is not doing a linear transition inside the material, but it's doing this random walk. And all these scatterings are estimated calculating this drift velocity, which is simply formula shown here, which is 5 millimeter per second. And the mean time crossing the 7.5 target centimeter of target is 16 seconds. And using this average time between the two collisions, which is 2.5 for 10 to minus 14, you can see that the value of the scattering is more about 8 order of grandness better than before. So the result at the end which we get is this 2.6 for 10 to minus 40. This includes obviously not only this scattering factor, but also some other improvements which this model described very well, but in this paper, because for time I have not time to explain all. So this should be the paper in which you can find more information about it. To conclude, I want to thank these two important associations which are financing us work also, John Templeton Foundation and the Foundational Questions Institute. And at the end, I want to thank you all for your attention.
Thanks a lot, Luca. Are there comments or questions?
Thank you for the nice talk. Maybe I missed it, but are you looking for a transition in which, in the final states, there are 3 electrons in the K shell?
Yes. We are looking for this kind of transition. It's not going. No. Okay. Yes, we are looking for this kind of transition, because the thing is that if there should be a violation and so a non-Paulian transition, nothing will give not to the electron the possibility to arrive to the 1s level, also if there are 2 electrons in that level. This surely will happen if there is a violation. But we have not found anything.
I was wondering, since the regular K-alpha transition is 8 kiloelectron volt of energy, while the forbidden transition has a lower energy. So I was wondering if I understood correctly.
Yes, it's a lower energy, but I said before that has been calculated with multi-configurational Dirac-Fock method, and the principal reason for this little bit decrease of energy is due to the fact that you have one more electron in the shell if you have this capture of violating electron. So this generated this, I move. This generated this this different kind of energy.
Okay, thank you.
Any other comment or question? If not, I have one actually. I was wondering, so you said that the CCDs are cooled down, and I was wondering how important is the stability of the temperature that you're keeping these CCDs, and which is the impact of any change in the.
It's fundamental because this kind of measurement, as you said, also because of the value of the limit, is a very precise measurement. So also a rise of temperature of this SDD of 10 Kelvin and 15 Kelvin can get can give more noise, and so give a problematic measurements, because you go to make a subtraction. So if you have, for example, in 7 days you have a rise of temperature in the detector, you should have bigger noise. When you make the subtraction, the result is not so precise and brilliant. So it's a very peculiar work. It's important. It's one of the most important things, I think.
How do you control the temperature? I mean, how do you keep it stable? Let's say.
They are stable using this liquid argon fluxing inside around this detector, but the details about how it has been done you can find in some publication. I have not done it, but the thing is that the other question about can we measure? We use some fitted cells to put it in this tube side of the detector to determine a temperature of this detector which is near to the real temperature, because obviously there is some distance between these PT cells and the slow control system which read them. But there should be around this temperature which I showed before.
Thanks a lot. Any other comment or question? Okay, if not, let's thank Luca again. And all the speakers of the session that is not over.
Thanks, Lydia, for sharing the session. So now it's a pleasure for me to introduce to you the Deputy Director of the Department of Physics here in Tor Vergata, Lucio Cerrito. Who will give us the official greetings for the department, and also Lucio will also give a short talk on how to be effective in asking for grants, which is a thing that I think every one of you will be useful.
So sort of. Let's see. Yes, I will actually. Yes, good morning. It's a pleasure for me to say a few words today on behalf, welcome on behalf of our Director of the Physics Department, and also share with you a few statistics about a topic which is somewhat dear to me, which is responsive grant funding, which should be somewhat familiar to most of you as young researchers. So no, I won't talk about how to be effective in grant proposals, even though that would be a very nice topic to discuss. But instead, I will. Sorry, okay. Instead, I will share with you some statistics and some information which I think is relevant for people who is at your stage of career, which usually is just after the PhD or a few years after the PhD, and you're making your way through the difficult path of working in the academic field. This is a table of Marie Curie fellowships between 2014 and 2020. What it shows is the breakdown of the fellows going to Italy. What it shows is the breakdown of fellows going to Italy, so coming to us as a number of countries of their own nationality. You see here, what we see from these tables, we learn where we are attractive, we learn where we have problems. Here you see, for example, Italy is an attraction for Italians, that's certainly true, and for Spanish and Greeks, but not much for anybody else. And here you see the Italian fellows as they go abroad in the UK, in Spain, US, in Italy, France, Germany, Netherlands, Switzerland, and so on. So this table, I'll show you a few more of these. But before I do that, I want to remind you what responsive grant funding is. You should be fairly familiar with it. It's a funding request responding to an open call. So with a number of requirements, a topic, a funding envelope, an applicant characteristics, perhaps age, not an graphical age, but number of years since PhD, host institution, and so on. It's judged by a panel of experts. It's still reviewed by referees. It's tension against other proposals. That means usually there is a competition for getting funding like these. The funding is awarded to the specific certificates for support. So this, broadly speaking, is what responsive grant funding is. Examples, and these are the ones which I think are more relevant for young researchers, are the ones ad hominem. That means funding given to you, not for a case, only for a case, but to a person. And these include a number of schemes, the Programma Vita Levi Montalcini for people stationed abroad who want to come to Italy, UK Science and Technology Research Fellowships, UK Royal Society Fellowships. These are actually some of the oldest schemes that have been going on for nearly 20 years. EMFN fellowships, there are a couple of types now. There are the proper EMFN, some are earmarked for foreigners, others not. There are the so-called Marie Curie fellowships, which is the graph that I showed you earlier. They have various types: global fellowships, European fellowships, and then there are the more, if you want, the more senior ones: European Research Council, starting, consolidated, and advanced. So this is a sort of list. It's not a complete list. So why is this important to you? Why it should matter? First of all, it gives you scientific independence. You choose what you want to work on. Often I meet people who, young postdocs, who apply to jobs and they say, well, now I got the job, can I work on this? No. Usually, if you apply for a job where there is a job specification, you have no freedom. You have to do what is written on that piece of paper when you apply. On the other hand, if you want to do what you want, which is what you should be doing, is you have to apply for funding for and argue that what you want to be doing is interesting and worthwhile funding. So it gives you scientific independence. You choose what to work on. It pays your own contract. You choose usually where to go, in which country or in which institution. So you get to pick the best places if you like. It builds a track record in your CV. It also gets used to think of why do I want to do this and why should I be doing this. And that's an exercise that is always useful. About every 6 months, you should be thinking, why should I be working on this? Is it worthwhile? Is it interesting? And why is it me? Why can somebody else do it better, for example? Why can I do it better than anybody else? It's also part of CV evaluations these days. So this is the Abilitazione Scientifica in Italy, but that's a similar case for other countries. So it's the indicators for scientific responsibility of research projects. So that builds up your CV and gives you some more points ahead of other people. So I already said you choose the theme of your research, pays your salary, plus usually additional expenses, travels, conferences, it gives you a little budget for moving around. It's an excellent opportunity for people just out of PhD or second postdoctoral experience. And as added bonus, it allows you to change institution from your PhD studies, which you should be doing. I strongly advise everyone to always change institution once you finish the PhD and go somewhere else, not to stick in your same group. So how much money are we talking about? We're talking about lots of money. We're talking about funding. This is just a breakdown from the European Union. Of course, this funding, 80 billion euros in Horizon 2020, so in a span of 5 years, 6 years, 2014, 2020. Of course, this is complementary to national funding. It doesn't replace national funding, but it gives a complementary source for things that precisely actually for these schemes which might struggle at national level. So this is a breakdown of how the funding for the Horizon programs, and they were called differently, how it's grown since 1984 to 2014, 2020, and the next one is even bigger than this. So there is money around if you know how to tap into it. There are, of course, problems, and the statistics I'll show you in the following are about some of the problems we have as institutions, particularly in Italy, with recruitment and with grants. But you should be aware of these things. You should be aware of where the problems are. You should be aware of the context in which you apply, so that you can maximize your chances. This is statistics, age distribution of the CRC grants. So far I talked mostly about early research grants, so the ones just after postdocs. So Marie Curie typically, or INFM fellowships, or STSC fellowships, they're first or second postdoc grants. So they're appropriate for, say, 1 to 4 or 5 years after PhD. After those, you can tap into these ones, the ERC grants. They come in 3 types. These are the standard, the starting grants, the consolidated grants, and the advanced grants. And this is the breakdown in age of application. They have constraints on how many years from PhD you have to be, but this is the graphical age. You see the peak is the age of 34. So before they see, you should be applying essentially for most of the other funding fellowships. Here is interesting. The majority is actually starting grants, even though the advanced grants are spread, but they're quite a number. But so there is a peak at about 33, 34. That means this arrow that I placed here is about the median age for permanent tenure track jobs. So most of the people who end up applying or winning these grants are normally so people with at least 6 or 7 years of experience in postdoc. And that's important also because these are the people that we recruit in universities as tenure track here in Italy as at the UB. So it's important to see what kind of people we hire, and there are lots of interesting statistics you can see from these grants. This is the latest ERC starting grant. The statistics is not high. This is only 1 year. This is 403 grants. And we always look at these breakdown. This is the number of grantees spread by nationality of the person. So Germany comes usually first. Italy comes usually between second, third, or fourth. In this statistics, if you apply croissants, and certainly here, these three are pretty much equal: Italy, France, Netherlands, UK. These are nationals. And then so on. So usually the distribution of nationalities follows the population share, and the Italian case is not different. So we actually look at, this is the population table. Germany has 82 million people, it's the largest. France, UK, and Italy have about 60 to 65 million people. Netherlands are 17 million. So we should expect to be, as Italian nationals, at around second, third, or fourth place in these tables, and that's usually the case. The Netherlands is actually a special case. It's usually much better than its population share. It's not just in this low statistic grants, and that's much to their credit. Here you also see another feature of these things. When a country goes up in GDP, that means it becomes richer, the attractiveness of going into the academic sector decreases. So this is the case for UK nationals. Many of the top PhDs go into, say, financial services or to technical services. So the university is not as much as attractive as it is for countries with slightly lower GDP. So that's another feature that you often see in these grants. Here is where we start seeing problems. This is the number of grants. It's a much larger statistics. It's 10 years of ERC between 2007 and 2015 plus the 2016 calls. So it's a lot of grants here. And what we see now, the breakdown is again about the hosts. However, you see Italy slipping through places down here. So first of all, let's see more in detail what this is. So the red arrow is nationals in their host country. The blue is non-nationals in that country. So that means how attractive that country university system is to foreigners, essentially. So you see the UK has a massive sort of number of grants from non-nationals, has a tiny proportion of its own nationals that go abroad. So that's a positive net influx of grants. Germany, on the other hand, has a different trend. So these are the nationals, the Germans in their own country. These are the non-Germans going to Germany to take these grants, and these are the Germans going out. So Germany has somewhat a balanced situation in which there is an outgoing flux of people and somewhat equivalent incoming flux of people. So the net is roughly unchanged, and they maintain a fairly high proportion of grants. Italy is the only exception to this entire trend. You see, this is Switzerland. It's also extremely attractive to non-Swiss people and loses just a tiny fraction of its own. Italy, I was saying, has almost all grants from Italians. It has a tiny fraction of non-nationals coming to Italy and a massive fraction of Italians going out. So this is the only case we see here in which you have a significant outflux and a negative, almost zero influx and a negative flow of people. So here is where we start seeing problems, which we as institutions should should be dealing with and you as applicants should be aware of. So this is another interesting graph. This is number of grantees by country of host institutions. And this is broken down into nationals hosted in home country, granting moving to the country, or staying in the country. So look at the UK. It has, as we were saying, the non-European grantees staying there. They were already working there. European grantees staying there, and the nationals in their own country. But the point here is that this dark brown part, these are the grantees moving to the countries. It's actually a small fraction. So when people apply to these grants, and when we're saying some nationals are working in another country, they are already there. They're not applying, winning, and then shipping off. So the key to this is how the people is actually recruited before. It's not so much being attractive to getting an offer for a position after you've got a grant, and so you take it back and go. So there's a frequent misconception here. The Italian grantees move to other countries because they have better conditions after they win these grants. That's a gross misconception. The reality is that they're already working there. They've been hired before they were winning the grants because somebody picked up on the value of these people beforehand, presumably 2 or 3 years beforehand. So is there a recruitment problem? And I put a question mark. I know I have my own guess that there is a recruitment problem in the way we do this, but it's worthwhile to investigate further. These are the success rates. Again, the largest statistics, 10 years. This is the percentage of grants that are successful over, so the number of grants successful divided by the number of applications, broken down again in years. And here you see something also quite disturbing. So the average success rate is about 12%. Some countries fare particularly better: France, Netherlands, Germany, UK, Austria, Belgium, Denmark. And here is Italy, about a third of the success rates. So, well, look at Switzerland, 22%. So, do they write better, or are they selected differently? I sort of fear that here again, the success rate being significantly lower than average is hinting to a significant recruitment problem. It's about half the success rate. It's as if we've lost half of the people who were going to win, and they went all abroad, and we haven't replaced them with nearly the same quality people to the ones that we lost. So that's, you can do the math. And this is another interesting table. This is share of foreign citizens among the academic staff. This is 2013. It only has a few countries, but it does have Italy. It's only 3% and significantly lower than some of those countries which had a much higher rates of successes. So Switzerland, 45%, UK, 24%, Denmark, Germany, and so on. These are the top institutions where they go to. There's no Italian institutions here, so that's a surprise. So, I mean, this is just to highlight to you some of the problems that we're seeing. I think there is a recruitment problem in the way we recruit junior people, but of course there is much more effort to be done, first to understand the problem and second to correct it. In the meantime, at your point in career, you should be applying for these things. No matter where you apply, whether it's in Italy or somewhere else, you should be applying. The usual feeling for people not applying is this imposter syndrome. I'm not sure if you're familiar with imposter syndrome. Imposter syndrome is where you go about and have this sense, this feeling that everybody else has actually understood something that you haven't, and you're sort of somewhat faking your way around and you're not quite worth it. This is how philosophers, so psychologists describe this. The imposter syndrome, this is what you think you can do, and this is what you actually can do. This is overconfidence, what you can do and what you think you can do. So that's not the goal. That's not what you want to do when you think, oh, I shouldn't apply to these things. This is what you should be doing. You should sort of resize what you think you can know and to the right, to the appropriate size, which actually not usually match what other people know. So it's a very, very important mindset. So that's all I wanted to say. Thanks.
Thank you very much, Lucio. If you have any time, maybe Lucio can stay with us during the networking coffee, so that if any one of you want to ask more about this, we can discuss during the coffee break. We reconvene here in half an hour, so 11:50. Okay. Let's go for the coffee in the other room. Thanks. Grazie mille. Ti lascio andare così. Sì, sì, sì. Sì, sì, ovviamente qui.
Poi non sono sì. Ricercano perché ci saranno devono essere piccoli cambiamenti di programma, visto se il share.
Ah, ok.
Non posso riuscire a vedere la presentazione dei vari. Sì.
Ci stai?
Sì, come si fa a andare avanti? Ah, sì, è andato. Ok, questo è avanti.
Sono lento? Ah no, non c'è da fare.
Senti, ma è possibile farti di dove studiare direttamente? Cioè, effettivamente non parlo io. Lo vedevo in immagine, ma non come...
Ma allora dipende dalla presentazione.
Tecnicamente,
Che non è...
essendo già nel sito del programma, c'è.
Ma se tu non funziona, non è che c'è quel file. Perché a seconda di come salvi il PowerPoint, o lui ti fa il video embedded e allora è proposto, oppure lui ti manda un collegamento e quindi giustamente poi non funziona.
Vabbè, sì, sì.
Ok,
Sì, non ti preoccupare. Va bene, sì. Basta che tutto funziona.
Allora,
che sessione?
Matter.
Questa è la
Matter
4.
Matter physics.
cancia la qualche parte. Ah, quindi non sono io. Matter 2.
Sì, Matter 2 della sessione 4.
Quindi, Gia,
Io, Claudia Simo.
Stina,
Prima.
ok. Non funziona.
Non è che il layout diciamo,
Ah, è quello inglese.
c'è il layout in italiano e stamattina la cosa è stata quindi
No, questa è una HDMI, non c'entra niente.
lui è diventato ultimo, non pensavo di
Adesso trovo
è vicino.
finale, certo, c'è scritto finale. Allora, F2. Allora, mi dici il numero?
21. No, 2, 3, 4, 5, 6.
Sì, 2, è lui.
Sì, però è diventato 5.
Ah no, ce l'abbiamo. Sì. Adesso vado, cerco Paola.
Sì, vado.
Sì, che io conosco. No, io ho tutti i
Io lo regalo sempre in river a lei.
Ragazzi, io i partecipanti di YRM
Ormai sono 22. Controllare ovviamente
Hai controllato
Sì.
le funzioni,
il problema
il dubbio.
Avete trovato?
No.
Legato a
Adesso arrivo anch'io, più che altro il microfono, perché dobbiamo avere 3 microfoni.
Guarda, dobbiamo solo ottenere la maniera diversa.
Ok, numerato, poi magari col mobile ci
Dobbiamo fare
muoviamo
così.
in sala.
Che
Il chairman parla lì.
parla qua.
Quindi
Il
Enrico
microfono.
parli là
Sì.
per presentare.
Sì.
Ok?
Se vuoi si può accendere anche quello.
Poi posso usare questo?
Allora no, dovresti usare, tu devi usare
Chi presenta, sto
ok,
qua,
ok,
quindi di volta in volta poi gli dici
Ok.
sì, il microfono.
e invece il mobile va per sala, per le
Il
donne.
gelato lo usiamo in sala. Quindi quello è questo pure.
Lei.
Aspetta, verifico. Paola, l'hai nominata? Sì. Cioè nel senso, c'è scritto Paola Monci.
Guarda la colonna di destra. Sì, sì.
Allora vado in
sono questi.
Manu, mi sai anticipare?
l'hai spostato?
Prima? No, sì, certo. Sì, già fatto, è tutto a posto. Scusami, non trovo
Sì, carata Vilera.
No, ma certo, no, Armando non me l'ha detto subito, no, eventualmente avremmo shiftato tutti, invece così è più facile per ricevere.
Che altro, devo ringraziarlo.
Allora, Armando e lui.
Aspetta, ti devo ringraziare.
Sì, anche questo sotto. Mazzalisi sarebbe qua. Prova, sente. Mazzalisi. Non faccio dare. E Zagaglia? No.
Ah, ok, devi avvisare. Mazzalisi,
sì, ok. Hai già provato se funziona?
L'abbiamo caricata prima, dovrebbe funzionare.
Sì, no, stavo vedendo giusto i PowerPoint. Se va.
Non ha effetti comunque o cose del genere.
No, di solito questo computer è abbastanza performante.
Sì, così. Solo slide.
Sulla destra.
Sì.
La versione sì. Mi pare che sia.
Passano un specchio, vedi.
Si inizia a vedere. Mi sa che non sto scrivendo.
Sì, è l'unico che si guarda.
No,
Ah, prendo il computer, la rimetto.
sì. Prova di trasferire.
Perché ho messo solo quello, ma poi è andato
cosa
storto.
storta. Sì, no, perché.
Ho fatto il computer.
Ok. Sì, certo c'è una penna qui all'inizio.
Magari sì.
Sì. E devi andare avanti. La cosa strana è che devi prendere la freccia in basso. No, perché ok, no, perché io per esempio vado sempre così e sbaglio. Quindi freccia in basso per andare avanti e rosso è
è controintuitivo nello stesso modo del mio, per cui...
Chi non è abituato che fa così, non funziona perché in realtà sta cercando di andare indietro, ma è la prima slide. Per cui funziona.
Lo metto direttamente qui.
Sì, sì.
Devi dire che eravamo avanti.
Sì.
Adesso il posto è stato spostato nella sessione A.
Ok. Ah sì, perché ci abbiamo qui. Oh, ma è sempre lo stesso numero?
Che mo te lo dico. No, è cambiato.
Che se no lo modifico.
Sarà la 14. Però ti dovrebbe dire...
Sì. Vabbè, poi dirò. Ok, va. Grazie.
E presenter
Sì, sì.
in basso, di là avanti.
Ah, in basso avanti e così il puntatore. Sì, infatti intuitivamente verrebbe.
Sì, no,
Devo andare sopra.
il mio in realtà è così, per cui non mi dà problemi.
Ah,
però
ok,
mi ha detto
sì, quindi sotto avanti.
Sì.
Poi riformato.
Sì,
Non c'è niente,
sì.
grazie.
No, non è, non è
guidare, perché dovevamo stare là nel 4, guarda quello che va e poi
Ah, ok, quindi
astrofisica, visto le cose,
non
l'idea mia.
no, non ho cambiato. Sì, io praticamente sono vicino al supporter e trovo le posizioni. Però vabbè, non sono un'altra cosa. Però sì, però sì, è cambiato. No, vabbè, vedete qualcosa che non era
No, ovviamente, però poi dico, c'è qualcosa che non va. Ripeto, se succedeva ieri non succede niente. Non è stato questa palla come però quella è la priorità. Non ho niente, guarda, io dipingo, Poi siamo qua, se siamo alla capo del
Li richiamo.
Quando mettono io applauso. Vediamo se funziona.